All right, awesome.
Right. So there you go.
Yeah, see?
Can you see him? I mean, I'll. Yeah. So the camera for you is here.
And Vincent, can you hear me if I'm talking?
Yeah, I can hear you well.
Okay, so if there would be questions, I would just, you know, uh,
Perfect.
say them
That would be.
for the people in the audience.
Yeah,
Have
that's very
any
nice. Yeah.
questions during the lecture or only at the end?
No, both are fine. Like, feel free to interrupt, feel free to ask questions whenever it's
Excellent.
appropriate.
I think that the audio is a bit on the. Oh, okay, good.
And yeah, so when Vincent starts speaking, can you just mute it?
Oh.
The mute is right. I mean,
Okay, so
yeah, when you,
so wait.
hang on a second. I think you're moving too fast.
Yeah, okay. So I'm muting myself, and here I control the volume. And okay.
I'm around.
And I guess we can pretty much start, right?
Oh yeah.
All right.
Morning. Okay, hi everyone. Thank you for coming. We're excited to have this day, the Diamond Day, and we plan to make this a recurring event that we have roughly once a year. And hopefully this could be a nice forum to bring the UK community in algorithms and complexity together and hear some exciting talks. Of course, due to weather and flights and cancellations and the usual things, we had some people that had to cancel, and in particular, we'll have to have the first talk in an online format, but the rest of the talk will be in person. Okay, so since we're a bit behind on time, let's start with our first speaker, which is Vincent Cohen-Addad from Google Research. Vincent has done some amazing work on clustering and networks and the foundations of machine learning. And today he will tell us about correlation clustering. So let's see if it works. Vincent, the stage should be yours.
Okay, thank you very much. Thank you very much for the hi everyone, and thank you very much for the invitation. I'm really sorry for not being able to join from physically. I mean, there was a lot of issues both from French and in the UK side. We had strikes and snow, so it's a tough combo. But hopefully I can visit Warwick in the future. Looking forward to be in person. And okay, so I'm gonna talk about this correlation clustering, the power of Sherali-Adams, and some new insight that we got from practice. It's a combination of works so one of them was at Fox and a couple of NeurIPS papers. So it's kind of like a new insight that we have got over the last couple of years on that pretty classic problem. And I think the exciting thing about this talk is that it's work in progress. So I'm really looking for ideas, for more ideas. I'm going to show you some ideas, but I think everyone can contribute at that point and have new ideas also that would help make progress on this problem. Okay, so if you have any question, please interrupt or shoot me an email afterwards if you feel more comfortable with that. And otherwise, let's start. All right. Cool. So in the correlation clustering problems, your input is a complete graph where each edge has a label, which is either plus or minus. And your goal is to find a partition of the vertices of the graph in such a way that you minimize the number of minus edges that are in the same cluster, where the both endpoints are in the same cluster, and plus edges, plus the number of plus edges where the endpoints are in different clusters. Okay, so if we and remember that the graph is complete and there are no weights. It's just the number of plus versus minus edges. So here, let me put in red the plus edges, in blue the minus edges. So let's make an example. In this case, we have a cluster here which only contains plus edges, so the cost is 0. We are very happy. And we have another cluster where only plus edges, so the cost is also 0, so we're very happy. And in between the two clusters, there are only like minus edges, so the cost is really 0. We're very happy. This is a perfect clustering. But if the graph is slightly different, like this would be another clustering where here you have a perfect cluster again, but now there are two edges that are two plus edges that are crossing, that are going across clusters. So my cost would be 2. Okay. So really, like here, think of plus edges are being points that you want to put in the same cluster, minus edges that points that you want to put in different clusters. Okay. And you want to minimize the total number of disagreements. It's a very useful model for clustering because, well, first it's for graphs, so graphs are everywhere, so it's very useful to have like a clustering model for graphs. But also it's like a little bit like you don't have too many parameters. You don't have to define in advance the number of clusters you want. It's really input dependent, like the number of clusters you can output. Cool, good. So we can use it whenever we have a pairwise similarity, like when we know that things should be together or things should be in different clusters. So it's also in active learning type questions. You may want to use that type of models. And one application is like if you have an entity graph on the web, you have many pages on Michael Jordan, but then like you can try to have like similarity notion between these different pages, and then computer clustering to identify who are these different persons. Okay, this is a very simple example. And now we want to study the complexity of this problem and what are the algorithms that can optimize this objective function. Okay, cool. So we have this problem since the early 2000s where there's this very classic paper that Vincent, Bloom, and Chawla who gave this like a constant factor approximation for this problem. Like the constant is very large, but it's still like a constant factor approximation. And there's been like a couple of several papers actually which improved it from this large constant to 4 and then to 3 and then to 2.5, and this was like early 2000s, still like 2005. And then for 10 years, nothing happens, and then finally like 2.06. And this is actually close to the LP integrality gap, the integrality gap of the linear program for the simple linear program for this problem, which is an integrality gap of 2, and I will come back to that later. And since 2015, nothing happened. And also on the hardness of approximation side, we know that if we believe P different from NP, then there exists a tiny epsilon for which 1 plus epsilon is impossible, is NP hard. Okay, so in this talk, we want to get a better constant factor approximation than 2.06 for that problem. Okay, and we know that the integrality gap of the LP is 2. Good. So okay, so there are various versions of the problem. So I'm talking about the complete version where we have the mean, so that's what I just described. There are other versions of the problem where you can try to maximize the number of agreements, maximize the number of pairs that you get correctly, like the number of plus edges that you put inside plus the number of minus edges you put across. It's a much easier problem, and there is a p-task. It's also much less useful in practice because in practice, like the number of mistakes is small. So if you get the 1 plus epsilon for the max, it doesn't say much for real world. Good. And then there is a general version where the graph is not necessarily complete, or you can add weights. And then the mean version is equivalent to multi-cut. So there is a log n approximation using multi-cut. But also, if you get better than log n, you will also improve the classic multi-cut problem. So it's going to be hard to do better than log n. So the two problems are actually equivalent. So it's there. And then for the max version, you can get to 0.766, and you can't do better than 0.87. So that's the status. And nothing has happened since 2004. So it's still like pretty hard open question like that. Okay, cool. So our result from so this is the Fox 22 paper that I'm going to present today. It's we showed that there is a 1.994 plus epsilon approximation that runs in time n to the 1 over epsilon. And so this goes below the linear program integrality gap. Okay, so you can do better than the LP. using this new algorithm that we introduced, and that is based on the Sherali-Adams hierarchy that I'm going to describe next. And of course, it's like the exciting thing about this result is that you can get below 2, so that's pretty cool. That this LP integrality gap is not the final answer. We can indeed go below. So it opens this research direction of exploring what's happening below 2. On the other hand, our running time is n to the 1 over epsilon squared, while the 2.06 approximation runs in time n cube or something like this, so it's related to n cube. There's a 2.5 that is even simpler than that. So it's like the running time is not as really good. But we care about the approximation guarantee, so that's okay. Okay, so to understand the idea behind our algorithm, and I think it's possible to understand 99% of what's happening in our algorithm today. So let me try to walk you through this. So for this problem, there have been a couple of algorithms that have been very successful, and they are essentially based on this pivot algorithm. And the pivot algorithm is very simple. You're given this graph, GV, which is a complete graph with the plus minus labels. And then you will do, it's a paradigm, right? So you will do this. You will do, I'm going to build one cluster, put it aside, remove it, that's one of my clusters, then recurse on the rest, and then pick another cluster, and then put it aside, and then recurse on the rest. So you build your clustering iteratively, one cluster at a time, okay? So that's the general principle. And the pivoting part is coming on which cluster you're going to build. I want to pick maybe randomly one cluster. I want to create this cluster randomly, take it, put it aside, and recurse on the rest. Okay, so what's a pivot-based algorithm for the simple pivot-based algorithm you can think about this for this problem is you pick a random vertex. Okay, so you pick a random vertex in your set of vertices. This random vertex belongs to some cluster, of course. So in the optimum solution, right? So you pick this, and okay, this random vertex is gonna be our vertex for creating this first cluster. Okay, so you pick it, and then you will choose a set S containing P that is going to be this cluster of P. Then you will take this cluster S containing P aside and recurse on the rest. Okay, and now if you sample this pivot vertex P, you say the next question you need to answer is how do you choose this set S of the cluster of P? Okay, because you have picked a random vertex, we are trying to build this cluster. Now, who is going to come with P in this cluster? Okay, so there are different ways of doing it. The natural way you would do it is that, okay, we have picked a random vertex P. Who should come with P? Well, all the plus neighbors of P, right? All the vertices to which P has a plus edge. If I have to build a cluster for P, that's a very good cluster because, it seems that, everybody who has a plus edge will come with P. Of course, maybe you have minus edges between the plus neighbors of P, which will incur some error. But in fact, one can still argue that this is a reasonable clustering. So in this example, if you pick P here, that will be your first cluster, then another P here, that will be the next cluster. But and then you get optimum, right? In that case, you will get an optimum clustering. The value will be 2. But if you pick this, if you are unlucky and you pick this cluster, this vertex P here, then you're going to bring together all these 3 vertices. So now that will be your first cluster, and your next cluster will be this one. So your total cost will be 3. Okay, so it's not optimal, okay, because you will bring these 2 vertices that shouldn't be together. They are both neighbors to P, but they shouldn't be together. So then you would have a higher cost. But that's life. Also, that these 2 blue edges, right? You will have these 2 blue edges together. Okay, cool. So, but still, you can. Sorry. No, I thought there was a question. Okay, so good. So you can still show that this is at most a 3 approximation. So this very naive algorithm, which is pick a random vertex, add all the plus neighbors to its cluster, make that a single cluster, move it aside, recurse. You can show that this is a 3 approximation. But it's something. Good. Now, what you would like to do next is have a better sense of who this set S of vertices that should come with P is. Okay, how do we set this the set S? And what we have said so far is a very naive thing. We just take the plus neighbors. Okay, so now what we are going to use is a linear program to get a better sense of who this set S should be. Okay, so let's look at the very simple linear program for the problem. It's very, very simple. Let me walk you through this. So we have a variable xij for each pair of vertices ij. Okay. And xij is 0 if ij are in the same cluster, and otherwise it's 1. Okay, 1 if they are in different clusters. Okay, so ij is going to be having the cost of 1 if xij is 1 and ij is a plus edge, because that means that you put the endpoints of a plus edge in different clusters, so you pay 1. Or xij is 0 if ij is a minus edge, because then in that case you put the endpoints of a minus edge in the same cluster, xij being 0. Okay, so that's exactly the objective that I'm writing here. So now this is very simple, like just minimize this number, minimize this function. But of course you can make it slightly stronger with this observation that if I and j are together, then j and k are together, and j and k are together, then I and k should also be together. Okay, so if I and j are together, j, k are together, then I, k. It's like transitivity, right? So you want this transitivity to be encoded in this LP, and how would you do that? Well, you say, okay, if I and k are not together, so if this was 1, then either ij are not together or jk are not together. Okay, so it's like if this is 1, then one of the two must be 1. This is a valid constraint, and it's a metric constraint. Like it says that xij, the xij variable should form a metric. It's triangle inequality. Good. So getting the solution with 0, 1 values for this LP is going to be NP hard, so we can't do it. But we can relax it and look at the linear relaxation and say, okay, xij are between real values between 0 and 1, and we want to solve this objective function. Okay, cool. And as I said, this is a triangle inequality, so it's like a metric space. Good. Okay, so that's the LP, natural LP, very simple. You just have to remember that xij equals 0, they are together, 1, they're not together, essentially. That's the only thing you have to worry about. And now we can get a solution, fractional solution to this LP. And now we can run the pivot algorithm again, but with this LP advice. Okay, now the LP is telling us some information. Okay, so again, we want to do this scheme. We pick a random vertex P, and then we are going to create the cluster of P. And now what we are going to say is, oh, let's look at the xij variables to decide who is going to come with P in this cluster. It's a very natural approach, right? Like what we're going to say that, oh, P is here. So now, A and P are very likely together because they are 0, 2. So you remember 0 is they are together, 1 is they are not together. So 0.2 means, oh, A and P are actually pretty close. So they are pretty much in the same cluster. 0 and 3, A, P, and D are more or less in the same cluster because like 0, 3, but like, B and P are like distance 0.7. So, they are not quite in the same cluster. Okay, so we are going to do that. So, we're going to pick P, and then any other vertex U, we are going to add it to S with probability 1 minus XPU. Okay. Remember that XPU is like, the distance. So 1 minus XPU is like the likelihood that they are actually together. Okay. Good. So now we do that independently for any other vertex U that is not P. Okay, that is still in my instance. Okay, and now we can show that this is indeed better. This is giving you, on average, a 2.5 approximation to the LP. So this is, better than the 3 that we had before. But now, like, we are getting like 2.5. So pretty good. And now that was done in 2005, and like 10 years later, this crowd came up and say, oh, okay, but maybe we can be smarter than that. And instead of just following blindly the LP's probabilities, we can do something slightly better. We can look at some function of the LP distances. And in fact, this function that they are using here says that, oh, if you have a plus edge, the way you interpret this LP probability should be different than a minus edge. I mean, this function is even more sophisticated than that, but one key idea in this paper is saying, oh, in fact, this LP probabilities, I can interpret them in two different ways depending on whether the edge is plus or the edge is minus. Okay. So good. So that's the key insight. And then this rounding here was very efficient because it got down to 2.06 times the LP. So very, very nice improvement. Remember that the LP integrality gap, and I'm going to come to that in a minute, is 2. So 2.06 is pretty good. Good. There is one important takeaway from these ideas here, and even the previous one that got 3, is that one way to bound and one key. Yeah, is there a question?
Yes.
No,
let's see if you can hear. Can you hear me? No, I don't think.
Yeah, I can hear you. Like if you speak loud enough, yeah.
We will try to speak loudly. So one question: how hard is the proof of the 3 approximation and the 2.5? They are kind of complicated case analysis based proof, or do you remember that?
Good, exactly. Okay, perfect. Thanks, Fabrizio, for this question. So good. I'm glad you made it to the UK. Like you were more lucky than I was. Good. So I hope you don't get stuck there. No, I'm kidding. So good question. So in fact, the analysis is exactly the takeaway. It's a very good question because exactly what my point was going to be. So the takeaway is that all these analyses, they are essentially based on analyzing each possible triangle. They are based on the triangle. So essentially what they are saying is that let's look at the triangle, any possible triangle of plus, minus, plus, minus, and so on, like all the possible combination of edges, labels on the triangle. And they say, okay, the worst approximation ratio you can get on a triangle is an upper bound on the approximation ratio of the whole algorithm. So it's they are losing something, right? They are saying something. They are doing something very crude here. They are saying like, okay, it's enough to look at what's happening for one triangle, and the worst possible triangle, that's going to be an upper bound on my whole algorithm. So it's a simplification. So in some sense, it's making the proof simpler because it's saying, okay, you just have to look at triangles to bound the overall ratio. But on the other hand, the thing that is frustrating is that, okay, now we are focusing on the worst possible triangle, okay? And the fact that it's the worst possible triangle, it's not very good because maybe you have only one bad triangle in your instance and all the other triangles are good. And now the whole ratio is just governed by these 3 edges. And whereas 99% of your edges are good. So it's not very good. It's easier for the analysis in some sense, but on the other hand, it's weakening it's getting a weaker bound. And also going back to exactly what Fabrizio asked, it's a little bit painful case analysis because now we have to enumerate over all possible triangles. Okay, so there are 3 edges, each has 2 choices. So it's 2 to the 3 or something, but you can break symmetries, of course, but it's 2 to the 3. It's still you have to look at all the triangles and and say, oh, what's the worst ratio for the triangles? And even then, when you look at what's the each triangle, you still have to show, it depends on the probabilities of the LP, right? So it's a sophisticated analysis because now it's the worst possible triangles over the worst possible choice of LP parameters, LP solutions. So you iterate over all possible triangles, all possible LP solutions. So it's a lot of case analysis. Yeah.
Okay, thanks.
Sure. All right. Good. So limitation of the LP. Yeah. So the LP has a very stupid integrality gap of 2 that I have said before, which is this very simple instance where you have a star like this. So all of these are plus edges, and all the other edges are minus edges. Okay, so it's like a star of plus. Okay. And now what's the optimum integral solution? Well, the optimum integral solution, it can only make one cluster essentially. Like, you know, it's going to make like everybody in a singleton cluster. Because if you start putting like, or maybe two of them would be in one cluster, but you can't have very large clusters. You can't have one big cluster here because you have too many minus edges, right? Like the number of minus edges is quadratic on the number of plus edges. So it's not very good in that sense, right? Like, so you can't have like more than one cluster. So essentially, you can't have like one big cluster. So essentially here, your cost is going to be roughly k minus 1. Like if your star has size k, you're going to have like k minus 1 opt. But then DLP can cheat a lot because he can put xip for all the edges here to be 1/2, meaning that each edge here is cut with property 1/2. And all the other edges that are minus edges, it could put them distance 1, meaning that now, you know, the distances are like, these are all minus edges with distance 1. So the cost is 0 for them. So it's paying half on all the plus and 0 on all the minus. So the cost is like k over 2. So there is roughly a, you know, factor 2 just on that instance, which is a pretty stupid instance because it's like a very clear case where we should have, you know, everybody on a singleton, or like, you know, everybody but 2 on the singleton. So it's not, yeah, it's a very trivial instance, but like here the LP is like, you know, completely fooled by this. Okay. So now we want to go beyond this 2. All right. So we need some sort of like stronger relaxation. Okay. So how are we gonna ask for a stronger relaxation of this for this problem? Well, we are gonna take this LP and try to strengthen it by looking at larger subsets. So one way to see this LP is that it's looking at pairs of vertices. So it's saying, okay, if I take a pair of vertices, that's the cost that the LP is going to pay for this pair of vertices. Okay, but now let's even ask the LP to tell me clustering on larger subsets. Okay, so let's fix a constant R. So let's think of this as being like 10. Okay, R as being 10. It's a constant, but it's not too small. Okay, and then we are gonna say that, okay, I will have a variable that tells me the likelihood of any clustering of these R variables, of these R vertices. Okay, so for any subset of size R, I'm going to have a bunch of variables that tell me the distribution of clustering over this subset of size R. Okay, so my goal. So if I look at this subset, okay, so this is a subset of, you know, a bunch of vertices, and now I want my Y variables to tell me, oh, if I look at this subset of 4 vertices, the clustering that puts A on one side, B on the other, B on another side, and CD together has likelihood 1, while the clustering that puts, like, you know, maybe A, B, C, D all together has likelihood 0. And A and B, A on one side, B on another side, C on another side, D on another side, 0. A, B together, C on another side, D on another side, 0. So essentially, I want that, like, you know, if this is my whole graph here, and my blue are these not the clusters, then the LP variable should indicate how the clustering behaves regarding on the subset of variables. Like, you know, what's the optimum clustering induced on my subset of variables? So here I'm looking at a subset of size 4, and so for these 4 variables, I want the distribution over clustering. Okay, so I'm now asking the LP to give me a distribution over the possible clusterings of the size R subsets of my instance. All possible size R subsets. And because R is constant, this is still polytime, okay? But, you know, I'm asking for, like, you know, possible clusterings. So essentially now we have, this is like, you know, if that's my opt, I can clearly, you know, express it as an integral solution here. If this is integral opt, I can really represent it here as an integral solution by doing what I just said, which is like, okay, just set this variable to 1 and the other to 0. Okay. Okay, cool. So number of variables is now n to the r, because I'm looking at all possible r size subset of variables, and I have like several, you know, variables for them, for the subsets, for each subset. And we have some consistency, which says that for, if we have a distribution of a clustering for a set of size r-1, then it has to be consistent. This distribution has to be consistent with the distribution of a subset for size r. Okay. So essentially, this says that, okay, if you have a subset S that of another subset T, and S is divided into S1, let's say up to SL, that's my tentative clustering, then, like, you know, the value of this variable, which is like the likelihood of this being the actual clustering of S, is the sum over all possible extensions of that clustering onto T. Okay, and T is a superset, so it's all the ways you would expand that clustering onto the size T subset. So that's how you make this consistency over different sizes, different subsets. Okay, good. So now we have this stronger LP. Okay, so that's the way it looks. It naturally implies the triangle inequality constraint. So it's just a strictly stronger LP than the one we had before. And essentially, you can interpret it as a Sherali-Adams hierarchy over the variables we had. Okay, and good. And now, right, and now essentially what we are going to say is that, okay, what we want to argue now is why is that LP better than the one we had before? Okay, why is it better than what people have done in the past? How is that LP useful? Okay, and here is the high-level interpretation of why this LP is useful, and then I'm going to try to convince you a little more. Is that, okay, how is the pivot scheme work? Like, how does it work? So you were picking a pivot P, and then with the previous approaches, people were doing this. Okay, I'm going to decide who is going to come with P in the following way. I look at any other vertex U, and independently of the others, I'm going to decide whether U should come with P or not. Okay, so I'm going to toss an independent coin for each U and decide whether it comes with P or not. Okay, but this independent coin is the only thing we have in the past, right? Because we only had variable xij, so we can only say, oh, okay, we have this probability between P and U, and that's the only thing we have in our LP. So now to decide whether P and U should go together, then that's the only thing we can look at. Okay. Now we have larger subsets. Okay. So what's important here is that in this example in this bad triangle example, you know, if let's say U is my pivot, then with probability half, I'm going to add V, and independently with probability half, I'm going to add W. So now you can ask, what's the probability that I put everybody together? Well, it still happens with a large probability, right? Because, you know, it's like, you know, oh, 1/2 that this guy comes, and then times 1/2 that this guy comes. So with probability 1/4, I'm going to put these guys together. But now we are saying something very important. We are saying, okay, LP, please tell me what's your feeling about this triangle. Are you telling me like, okay, you're telling me 1/2, 1/2. What does that mean? Does it mean that you have UV together with probability 1/2, or UW together with probability 1/2, or everybody together with probability 1/2? Okay, and these are three different things, right? Like if it's UV with probability 1/2 and UW with probability 1/2, but these two events are orthogonal, like, you know, disjoint, it's a different thing than telling me, oh, with probability 1/2 you put everybody together, and with probability 1/2 you don't put everybody together. Like, you know, you put them in different clusters. So these are different, you know, events, right? So I want to be able to tell them apart. But if I just have the xij variables, I can't tell them apart because I just see one half here, one half there. But now that I have probability distribution over clusterings for subsets, in particular for triangles, now I can look at my LP and I can see, oh, I actually want VU with probability 1/2 and UV with probability 1/2, and that's it. So these are two different things, right? So now I can look at that in the LP. So okay, so now the LP can tell us V and W are always separate, or like they are not. And now instead of doing things independently as we were doing it in the past, like deciding whether V should come with U independently of whether W should come with U, we're going to try to do it with some dependencies. Okay, we're going to try to look at better model the events that are happening in the LP. Okay. So now what we are doing is that we are essentially doing a correlated rounding, which is based on a bunch of lemmas that were developed for the unique games conjecture and CSPs more generally to get better roundings for CSPs. And what we are saying is that we are saying, okay, we are taking a pivot U, but then what we want is that we want this conditional probability. We want to be able to create the cluster of U based on the residual probabilities of things that have already happened, and we want the right probability space here. And so what we are going to use is this theorem that says that for any U, we can sample the subset S of arbitrary size such that the probability that V and W are in S minus the probability that U, V, W are together in the same cluster, in the same probability distribution, that they end up together, is almost the same. Is almost what we expect it to be in the these two numbers are almost the same up to this additive epsilon. So on average, that says that on average for two vertices VW, the probability that they get into my cluster S is exactly what's happening in the LP plus this tiny epsilon. But note that this epsilon is an absolute constant, so we have to worry a little bit about it because maybe that was 0 and now we are getting epsilon or something, so it's not very good. But it's still we are trying to now look at subsets and we are saying, okay, things happens nicely for that subset. Okay, good. And so that's what we have for 1/epsilon² rounds of Sherali-Adams. That's what if we have this consistency up to 1/epsilon² size subsets, then we can have this formula. So that's why we have this 1/epsilon² rounds of Sherali-Adams, and we have this additive epsilon here that we have to work in our proof. That's kind of challenging, but that's still something. And if you use that analysis on the triangle Bayes analysis, you will get the 2 approximation. Okay, and you can show that in this example we are getting 2. So it's just this example here. If you just look at this example, this is a valid solution even for the Sherali-Adams LP, right? Because it's only 3 variables. So this is still feasible. But it's not like an integrality gap of 2 because the cost is 1 and the opt cost is also 1. So it's not a counterexample. But essentially the triangle Bayes analysis has some limitation. And the limitation of the triangle Bayes analysis is that even if we use this more amortized way and correlated way of rounding, we still get the 2 approximation. So then we have to deal with more sophisticated. Okay, so let me say one thing before I go to the next slide. But then we have to do something slightly more to get below 1.994, and this slightly more is going to be amortizing by saying oh, there are not so many bad triangles that are tight at 2. So, but still, with this analysis, there are triangles for which the ratio is going to be 2. Okay, so the actual rounding algorithm that we have is essentially going to ensure that the cost of the algorithm for any triangle PUV is at most 2 times the LP cost for any triangle for the triangle PUV. That's essentially what we have. All right, there's a question? No, no question. Okay. No, okay, good. So, but this is not quite true if you do the naive correlated rounding. So we need to do something slightly more. But essentially, the final algorithm is this one. We choose P. We apply the correlated rounding to the plus neighbors of P, whose LP's values are bounded away from 0 or 1, because otherwise this additive error becomes like a mess. So we take them for like bounded away from 0 and 1. And then for the other one, we can do independent rounding, because you can think of it as like, oh, if things are close to 0 and 1, well, independent rounding is pretty good already, because they are already pretty close to 0 and 1. So they are pretty extreme events already, like, they're pretty clear events. So it's fine. It's more for the things that are in between that we don't know and we need correlations. And then for the minus edges, we need something different, because, it's different thing. Like minus edges behave differently. So we also do independent rounding for the minus neighbors. Okay. And essentially we can get like these two approximations. And this is also a tedious case analysis that, we need to carry over. And it's probably not the proof from the book. It's like, very bad. I mean, it's not very bad, but it's like the only way we know how to round it, but still based on triangles, which is not very nice. And it gives even more case analysis. So it's not as clean, not very clean. Okay, cool. So the full proof, I'm gonna just, give you like, two bullets. So as I said, like this gives you two approximation. And now if you want to go below 2, then we have to average and say that, okay, there are bad triangles for which we get 2 approximation, but on average, there cannot be so many bad triangles. And so, because otherwise it's not feasible. Like there's a graph theoretic idea behind it that says, okay, if you are below, if you can't have too many bad triangles. Okay, cool. And that was it. And essentially that gives us like a 1.995 roughly approximation for population clustering that go below 2, and that give essentially new techniques using this correlation clustering agents. And I think I'm running out of time, so I won't go too much into I won't go at all in the practical stuff. And like, we can, it's for future talk. Like next time I can come to Warwick, I'll talk about the rest. All right, thank you very much. And I'm gonna, I'm gonna stop here. I have a bunch of, open problems that I can ask. And, but like, maybe I'm already out of time. So maybe I'll share the slides and you can look at the open problems. Thank you.
Thank you, Vincent. Any questions for Vincent? Yes, Mike?
Hello, Vincent. Nice talk. This is Mike Patterson. One possible weakness of the algorithm seems to me that you're still choosing a vertex uniformly at random. Is there any possibility of getting a better result by choosing a vertex, seeing how the first cluster goes?
So I can't hear very, very well. So can you speak a little louder or?
Shall I go closer? Yeah. I'll try going closer to where the mic is. Is that any better?
Yeah, it's much better. Thank you.
In your algorithm, you choose a vertex uniformly at random and build its cluster. Is there any possibility of seeing how that cluster goes, and if it doesn't seem to work out too well, then try choosing another vertex at random?
Yeah, I mean, that's a great question. I was thinking about that, like, a couple of weeks ago, and like, maybe some sort of rejection sampling, like, you try some point, and then like, depending on how it goes, you reject with some probability. I think that would be great. I don't really know how to make it work. I don't know how to make it work.
Sounds as though the problem would be that the analysis would become impossibly difficult.
Yeah, exactly. The analysis becomes tricky. Also, I'm not exactly sure what would be the right rule for rejection. Like, when do you reject the cluster when it's okay? So there are very nice criteria that says, like, maybe if the cluster you create doesn't have like, a large enough number of plus edges inside, then you know that it contains many minus, and then it's a very bad cluster. So you might reject it anyway. But if we want to distinguish between a cluster that can give you like let's say a 2 approximation or like a 1.9 approximation, then I don't know what's the right cutoff to reject a given cluster. for example. But that's also something I don't know how to do.
Okay, thank you.
But it's a great question, yeah. Sure. I mean, actually, maybe even to simplify things and push that direction, maybe just using the natural pivot algorithm, like just the 3 approximation that doesn't look at the LP at all, that just take a random vertex and look at the plus neighbors and create a cluster. I think analyzing it with rejection sampling or with any other technique for resampling if some things are going bad, then I think that would be, it's probably simpler than dealing with the LP, but like, I don't know how to do it, and it's probably a very good question, yeah. And actually, maybe one of the open questions is that I wanted to mention is like getting a better than 3 approximation with an algorithm that is not an LP based, not LP rounding. That I think is a very good question. Like getting a fast better than 3 approximation without LP. That's great.
Okay, so thanks again for the excellent talk. Yes, and
sure.
Let's go to the next session.
Thank you, guys. Thank you, everyone.
Thank you. Hope to see you next time in Warwick.
Yeah. I wish I can come next time. Yeah, we should figure out something for the spring.
Excellent.
Thank you.
Bye-bye.
Bye-bye.